In this video, I introduce solids with similar cross-sections, and I show you how to compute volumes of revolution using the disk method and the washer method. Before we dive into our applications, we need to review a small thing. Suppose you have a function that's defined on a closed interval from a to b. Recall that you can subdivide that interval from a to b into n subintervals by using a partition. Now, in the kth such subinterval, where k goes from 1 to n, denote the length of that subinterval by change of x sub k, and also choose some value c sub k in that subinterval. By making these choices and forming the product of the function value at the choice times the length of the subinterval, and then just adding up those products, we form what's called a Riemann sum. Now, Riemann sums can vary a lot because you can subdivide the partition lots of different ways, and you can make your choices lots of different ways. But if you are able to limit how much the Riemann sums can possibly vary by simply limiting the partitions to those that are such that the longest such subinterval is fairly small, then we'd say that the limit of the Riemann sums exists, and it's defined to be the value that they all approach. In this case, we call it the definite integral from a to b of f of x dx. So there's Riemann sums, and then there's a limit of Riemann sums. And the limit of the Riemann sums is what we call a definite integral. Remember, the definite integral is a limit of Riemann sums. It's just we're very lucky that there's a better way to evaluate it by using the fundamental theorem of calculus. There is one thing we need to note here, though, is that we don't know when the limit exists, so we have this nice result that as long as you have a continuous function defined on a closed interval, then the limit of the Riemann sums always exists. The definite integral exists. Let's just do an example. So suppose that we subdivide the interval from 0 to 2 into n subintervals, and we denote x sub k as the rightmost x value in the k subinterval. I want to know what's the limit of this particular Riemann sum. Now, this is not difficult because if you notice, the function f of x equals x squared plus 6x is continuous on the interval from 0 to 2. So just by definition, the limit of this particular Riemann sum would have to then equal the definite integral from 0 to 2 of x squared plus 6x dx. Now, we know how to find that value without doing the limit process because of the fundamental theorem of calculus. So I can then replace this particular definite integral with the antiderivative, just evaluate from 0 to 2. And I evaluate the expression at 2, I evaluate the expression at 0, and then I subtract those results, and I get the answer. So the limit, as the norm of the partition goes to 0, of the summation, as k goes from 1 to n, of x sub k squared plus 6x sub k times the change of x sub k, that has to equal 44/3. Now, you might wonder, why would we go through this again? After all, we can find the value of the definite integral just by using the fundamental theorem of calculus. The reason is because almost always our applications start with Riemann sums, and we need some way to transition using the limit as the norm goes to 0 to a definite integral. Now we have enough to begin a simple application. First, some definitions. Form a cross-section S of x of a solid S by intersecting the solid with a plane perpendicular to an axis through a point x on that axis. Also assume that the overall cross-sections exist as long as x varies from a to b. Also associate to each such x the area a of x of the cross-section S of x. If all the sections are similar figures, then we say that the solid has similar cross-sections, and we can use some clever integration in order to find the volume of the solid. So let's go and find the volume of the solid by just going and slicing it into pieces and find the volume of all the little pieces. And in each case, we'll actually go and approximate the volume and just add them up. And then in the limit, find out what the answer is. So to do so, if you remember, there was an axis that we used to form our cross-sections. The plane was perpendicular to this axis. And the particular x values we could use to get the cross-sections was from a to b. So just partition that interval into n subintervals of whatever length. And then just slice the solid at those x values, x sub naught, x sub 0, x sub 2, x sub 3, up to x sub n. And then notice that between two cross-sections, you get a slab of the solid. I want to approximate it. Well, if these two cross-sections are really close together, then they can't change very much. So I'll find the area of one and just multiply it by its thickness, which would actually correspond to be the change in x. And you get this particular solid. Notice it's not the same as the slab I'm after, but it is a fairly close approximation as long as the two cross-sections are close to each other. So we find that the volume of the kth such slab is about equal to the area of the x sub k cross-section, that's A of x sub k, and then we multiply it by the thickness of the overall piece. In this case, the thickness is just a change of x, the distance between those two x values. I just do this for every single two consecutive x values in this partition to get that the volume of the solid is about equal to the sum of all these little slices I've made. Well, if we also assume that the area function is a continuous function as x goes from, well, a to b, then we can say that the limit of the Riemann sums would equal then the definite integral. And just think about it. If you were to take this object and slice it into really super small layers, each little piece is not going to be so the top and the bottom are the exact same size, but they'll be so close to each other that the approximation for each piece is incredibly good. So the summation doesn't have a whole lot of error, and the error should become less and less the thinner we make our slices. So it seems reasonable then to say that we will define that the volume of this solid is equal to the limit of these Riemann sums, and is therefore equal to the integral from a to b of a of x dx. Remember, think of it this way. You're going to take some kind of, in this case, a representative element that has, at an x value, a cross-section whose area is a as a function of the x that made the cross-section. And then you're going to multiply it by a thickness, dx, to get a solid. So literally, this integral says, sum up the small little volumes. The volumes being a of x times dx. So let's do an example. Define the region R to be a region in the xy plane bounded by the two curves y equals 4x minus x squared and y equals x squared. The solid S is going to have that as a base, so the base is flat. And if you ever take cross sections perpendicular to the x-axis, when you take that cross section and chop it into the object, it will make a square. I want to know what is the volume of this particular solid. So first, pick an x value, and think of that's your plane, and chop it right through the object. Notice I get a little line. Unfortunately, a line is not something you can see. You can't really see it. So I'm going to pretend that my slice has a little bit of thickness. That little bit of thickness is dx. So then I'll make a square, but with a little thickness. There you go. There's the object. So the cross section is a square, and the thickness is a small dx. Notice if I pick different x values, I wind up getting just different small little slices. So I want to know what's the area of my particular cross section. I want to know what a is a function of x. Well, the cross section is a square, so if I knew the side s, I could easily find the area, because the area would then be just the side squared. But I need it to be a function of x, not s. So notice though that line segment was actually the distance between 2 points, from the y coordinate in blue to the y coordinate in red. If I just subtract those y coordinates, I would get the actual length of that segment. That's what s is. So s has to be 4x minus x squared minus x squared. Notice I took the larger y value minus the smaller one. Also notice that as x changes, the red point is always above the blue point, so the subtraction is always positive. Well, that would then mean that the area as a function of x would have to be that length squared. that also means then I have an expression for the volume of that little bit of piece. We usually call that dV, so the small bit of volume is dV, and it's equal to the area times the thickness, dx. By summing up both sides using an integration, you get that the volume has to be the integration from 0 to 2 of the quantity 4x minus 2x squared, that quantity squared, times dx. So I think what we should do is actually go ahead and crank out that particular integration. So in order to find this particular definite integral, notice that we're going to be forced to just square this out first. So we have from 0 to 2. Distributing that particular product would then give you a 16x squared. You'd have minus a 16x cubed, and then plus a 4x to the fourth dx. That would then be equal to, you'd have 16 over 3x cubed minus 8x, 8. You'd have 4x to the fourth, and then you have plus 4 fifths x to the fifth. And we evaluate that from 0 to 2. So if you plug in 2, you would get 16 thirds times 8 minus 4 times 2 to the fourth. Now that would then be 16. And then I have plus 4 times 4 divided by 5 times 32. And then all I have to do is just add this up to get the answer. We can cheat though if you want to see a couple little tricks here. Notice that you can actually divide each of these terms by, well, at least 4. Yeah, you can divide each of them by 4. You can divide each by 6. You can divide by each by 13. 32. So actually you can divide each by 64, it looks like, because this 16 here, this is actually 64 times 2. While this is 64, and this is all over 3, and this is plus, this would actually be 2 times 64 all over 5. So you could then take out the 64, and you'd have left over a 2 thirds minus 1 plus 2 fifths. So if we write that as 64 times, using common denominators, you'd get 15. This would then be 10 minus 15 over 15. That'd be plus. This would then be 6 over 15. So you would get 64 times over 15. You get 10 minus 15, that's negative 5, plus 6, that would then be 1. So the answer should be 64/15, assuming that I did that arithmetic correctly. Let's do it again. So this time our solid will have the same exact base. It'll still be the same region, same curves, but this time the cross sections, when taken perpendicular to the x-axis, will not be squares, but this time they will be equilateral triangles. So let's pick an x value and look at that cross section. Well, this is edge on, so you can't really see it. So just like I did last time, I'm going to pretend there's a little bit of thickness. I'm going to exaggerate the picture, so the thickness is dx, and I'll draw in my triangle so it's kind of off to the side a little bit. There it is. I want to find the volume of that little piece. To do that, I need to find the area of an equilateral triangle. Well, if I knew the length of the side, if I remember my trig, the area of a triangle is 1/2 the product of the lengths of the two sides times the sine of the angle between them. In this case, that would then mean the area as a function of x would be 1/2 s times the sine of the angle between those two sides, which in this case, being an equilateral triangle, the angle must be 60 degrees. So we get the area as a function of x is the square root of 3 divided by 4 times s squared. And to find the length of s, that hasn't changed. All I do is look at the 2 points, and I look at the 2 y-coordinates, and I take the larger y-coordinate minus the smaller one. So that the s hasn't changed at all. That then means that the area of that equilateral triangle as a function of x is given by this formula. And I can find the volume as I always do. I just integrate all those pieces, multiply the dx to get the thickness, and I integrate from 0 to 2. This is the exact same integral I did moments ago, but with a constant involved. So it's just the same answer I had before, just multiplied to the square root of 3 divided by 4. Let's just do it one more time. We'll use the exact same region, but this time the cross sections are going to be semicircles. So here is my X, here's my slice. I once again will assume that the thickness is something you can actually see. The thickness is dx, and I'll look at it sideways a little bit. You should then see the semicircle with a little bit of thickness so you can actually see the picture. Well, I want to find the area of that semicircle as a function of x. Well, I know that has to be 1/2 pi times the radius squared, 1/2 the area of a circle. But the radius here would have to be, well, if you double it, it has to be the diameter, which is s. So then r is the diameter, s divided by 2. By plugging that in, I get the area as a function of s. It's just pi over 8 times s squared. And as we've done before, we know what s is, so we know what the area is as a function of x. That means then if we just integrate that from 0 to 2, we have the volume of our particular solid. Now, a very common solid with similar cross-sections is called a solid of revolution. These are often formed this way. We have some kind of function. In this case, pretend it's always above the x-axis for now. We call that function f of x. And look at the region between the graph and the x-axis. We're going to take that region defined over the interval from a to b, and we're going to revolve it around the x-axis. Now, when you do so, you should notice that if you take that solid and were to chop into it with a plane perpendicular to the x-axis, you always get circles. So, using what we've seen so far, I'm going to pick an x. This time though, I'm going to do away with the line, and I'll just go jump to the, here's a little bit of thickness, just so that you can see the picture. So the thickness is dx. That's a change in x values along the x-axis. That particular rectangle there, when I rotate the region, I rotate the rectangle. If you do so, you get a disk. Now that disk will have a radius, we'll call that r, and the cross section will have an area, and the volume we'll say is dv. The thickness of that disk is dx. I want to know then, what's the area of that cross section? Well, we know the area of the cross section would then be pi times that radius squared. All we need to do is now find out what the radius is as a function of x. Well, but the radius though, notice it's the difference between two y-coordinates defined by the rectangle. One point being a point riding the graph. The other point is actually always on the x-axis. So those y-coordinates are f of x and 0. That difference then is just f of x. So that means that the small amount of volume generated by this itty-bitty disk is the area times the thickness, dx. But the area is pi times the radius, being the function squared dx. So the dv is therefore pi times the function squared dx. If I just sum that up using integration, we get that the volume should then equal the integration from a to b of pi times the function squared dx. This is called the method of disks, and it's a way for us to find volumes of solids of revolution. And there's other variations, of course, but this is just the first one you're introduced to. So let's go ahead and try one. What is the volume of the solid of revolution formed by revolving the region in the first quadrant that is also bounded by the graphs of y equals x squared and x equals 4 about the x-axis? Now, to do a problem like this, typically you draw the region first, and you might notice I drew a pretty exaggerated version. The reason is I want to be able to draw inside that picture. Next, I pick an x value. Now, once I pick that x value, normally I would draw a line, but instead I'll give this line a little bit of thickness to make it be a rectangle. Now that rectangle will move back and forth to the left and to the right with its x values. I'll put the x on the inside. The rectangle then will be defined by where it were to meet the upper curve and where it would meet the bottommost curve that defines those two boundaries. Now I'll need at some point this y value, and I'll need at some point this y value, and the thickness of this rectangle is dx. So in order to find out the volume, since I'm using the method of disks and I'm going about the x-axis, I'm going to need this radius. So that radius winds up being the difference between those two y values, the uppermost y value and the bottom or lowest y value. Now we know what those y values are. In this case, every single point on this upper curve satisfies the equation y equals x squared, and every point on the lower curve is defined by y equals 0. So the r must be equal to x squared minus 0. That, of course, would just be x squared. So the small amount of volume generated by that one little rectangle as it goes about the x-axis, making a disk, would then be pi times that radius squared. That would be the cross-sectional area. And then I multiply it by the thickness dx. So that is pi times x squared squared. That's x to the fourth dx. That's the small bit of volume that that one rectangle generates. So if I want the overall volume, it would then equal the integration from 0 to 4 of pi x to the fourth dx. And I know it goes from 0 to 4 because this is where 0 is and this is where 4 is on the x-axis. We can, of course, do that integration very easily. That would then be pi over 5 times x to the fifth from 0 to 4. So that would be pi over 5 times 4 to the fifth power, which honestly I don't care about doing. But I suppose, let's see, if I do 4 to the fifth power, I would get 1024. Right, that's how it goes. So this would then be 1024 pi over 5. And that's the answer to that problem. Let's try it again. Let's find the volume of the solid revolution formed by revolving the region in the first quadrant and bound by the graphs of y equals the arctangent of x and y equals pi over 4 about the y-axis. Now this is a little more interesting because we're going about the y-axis, not the x-axis, but the ideas are the same. This time, going about the y-axis, think of it as partitioning the y-axis or a portion of it. To figure out what portion we need to partition, take the region and crush it against the axis we're going to be rotating about. So that would then be right here, this interval. Notice that goes from the y value of 0 to the y value of pi over 4. So this would be pi over 4, and this would be 0. Now, in this range, pick a y value and draw a line. So then this would be y equals something. But give that line a little bit of thickness. So it looks kind of like this, like a rectangle. This rectangle will move up and down with its y value. And notice there's a rightmost point and a leftmost point. I'm going to need those x values at some time. Now, did you notice that when I did it the first time, I had x in the middle and I had y's on the outside? Here it's just the opposite, y in the middle. That moves it up and down. And the x is on the outside. So eventually, if I take that particular rectangle and rotate around the axis, the y-axis, that would make a disk. So I need to know then, what is this distance? That's r. So the radius then would then be the rightmost x value in that rectangle minus the leftmost x value in that particular rectangle. So that would then be, let's see, this curve was y is equal to the arctangent of x. So if I take that equation and solve for x, I get another expression that represents that equation. That would be x equals the tangent of y by just taking the tangent of both sides. So the rightmost x value is the tangent of y minus the leftmost x value. Well, that's this point right here is on the equation x equals 0. So that's just 0. So then the radius is given by the tangent of y. That's good because we want it in terms of y this time. Because the thickness is a change in y. So we'll be integrating in terms of y this time, not x. So the small amount of volume would then be the cross-sectional area. That'd be pi times the radius squared times the thickness, which would then be dy. That is pi times the radius squared. That's the tangent squared of y dy. That's the volume of that one small representative element that represents all these different little disks that we would make. So the overall volume would then be the integration from 0 to pi over 4, as that is what y can range over, times pi times the tangent squared of y dy. We need now to find out what the value of this definite integral is. Well, we don't have an antiderivative for the tangent squared, but we recall, though, that there is a way to rewrite it as a sum, and that's usually one of the little tricks we want to use with integration if we get stuck. Write it as a sum of things we can integrate. This is the same as pi times 1 plus secant squared. Oh, well, no, let's try that again. It's actually secant squared minus 1. Fucking Christ. Let's just start that part over. Now, as of right now, we don't know how to find this particular... So let's find the value of this definite integral. To do so, I need to know the antiderivative of the tangent squared, which we don't know. We don't have that memorized. But we do know that there is a way to rewrite the tangent squared of y by using one of the trigonometric identities. This is then equal to 0 to pi over 4 of pi times the secant squared of y minus 1 dy. That would then become the pi antiderivative of secant squared, that is tangent of y, and then we subtract the antiderivative of 1, which is y, and we evaluate this from 0 to pi over 4. So this would then be pi times the tangent of pi over 4, that would just be a big old 1, minus, you would then have pi over 4. And if you go ahead and plug in 0 into that expression, you also get 0. That is the answer. You, of course, can multiply the pi through or simplify the fraction if you wish, but that is the answer. Let's go back and look at a region we've already seen. The region bounded in the first quadrant by the graphs also of y equals x squared and x equals 4. But this time, let's not revolve it about the x-axis. Instead, let's revolve it about the line y is equal to, x is equal to 4. So that would then be right here, x equals 4. And we're going to go about that line. So, like we normally do, I would then go and compress or project this object upon an axis, but instead of projecting upon the line x equals 4, that's a number line, but let's go project it upon the y-axis, as it's basically the same thing. So that would go from 0 to, I don't know, we'll have to figure that out. Now, but if you think of it as we take a very small y value, and from that y value we draw a line, I'll make it be a little thicker, add a little dimension to it, makes it easier to see. And on the inside, I'll put the y value. So then as the y value changes, that rectangle would move up and down, and the length of that rectangle would also change. The thickness, though, is always the same. The thickness is always dy. Notice there is a leftmost point and a rightmost point. I need to know eventually what this x value is here, and I need to know eventually what this x value is here. I'll need the radius. So the radius would then be the rightmost x value minus the leftmost x value. So the rightmost x value, well, this point off here to the right is always on the curve x equals 4, while the point on the left of that rectangle is always on the curve y equals x squared. So I need to know what x is equal to. So I'll just solve that for x to get x equals plus or minus the square root of y. You can't use plus or minus. In this case, the y must be always positive. So I would write down the square root of y. So the rightmost x value, that is 4. The leftmost x value, that is square root of y, and I subtract them. So the small amount of volume would then be equal to pi times that radius squared times the thickness, which right now is dy. So that would then be equal to pi times 4 minus the square root of y squared dy. So the volume is then equal to the integration from something to something of pi times 4 minus the square root of y, that quantity squared, dy. The lower bound is certainly 0. To find the upper bound, notice that this y value corresponds to what happens when you take this point and compress it or project it upon the y-axis. So the y-coordinate of that point is the y value I need. This point must be, the x value is 4, because it's on the line y equals 4, but it's also on the line y equals x squared, so the y-coordinate is 16. So the integration goes from 0 to 16. That's it. This time I won't do the integration, I'll just set it up. It's done like the others. You would just square this out, turn it into a sum, and then integrate each piece. Now you might have noticed in the examples I've given you so far that every time I drew in my rectangle to represent a portion of the region that I was going to revolve around the axis, that rectangle was always touching the axis of rotation. That way, when it touches and rotates, it would make a disk. Let's change it a little bit. This time our axis is not touching the region, and let's see what happens. So I want to take this particular region and rotate around the x-axis. It's defined between the lines x equals a, x equals b, and the two graphs of f of x and g of x. So once again, I'll project this object upon the x-axis. Then I'll pick an x value, and from that x value I'll draw a little line, getting myself a cross section. But I'll give it a little bit of thickness so that you can see it. When you do so, though, you wind up getting a rectangle that does not touch the axis. Now that's not good, because if you take a rectangle out here and rotate around the line, when you rotate it, there's a gap, there's a hole. And in fact, if you draw it, you wind up getting that. It's a disc with a hole in it, like a washer. Now it's easy for us, though, to find the volume of that washer. All we do is we find the volume of the outside disk, we find the volume of the inside disk, and we just subtract those volumes. To do so, I need the two radii of the circles that define this particular washer, the outer radius and the inner radius. We'll call them capital R and little r. So the volume of that disk then would then be pi times the outer radius squared minus pi times the inner radius squared. All I got to do is to figure out where are those distances in the picture. Now, unlike every other time, normally this would be the height of the rectangle. It's not this time, because it's from the outermost point of the rectangle to the axis. So that would then be that one. Now notice, if you think about it, it's like I'm rotating that red rectangle around and then finding its volume. The inner radius is from the closest point on that rectangle to the particular axis of rotation. That will then give you this rectangle and that little radius. And notice it's like I'm rotating that rectangle, that little orange rectangle, around the axis. So essentially, what we wind up doing is doing the problem of the method of disks twice, one for the outermost y value, one for the innermost y value, finding those separate volumes, and then just subtracting them. Well, but we normally would not do it as two integrals. That's kind of a waste of algebraic potential. It's possible that when you go and square these two functions and subtract them, that they might have common terms. If they have common terms, there's no reason for you to go and, well, integrate them twice. Hopefully they'll cancel or they'll combine in some way. So we only do one integral. This is the formula for what we call the method of washers. It's essentially the method of disks, just done twice. Now notice in the picture, at all times, the outermost point on that rectangle is always farther from, the inner one. If that ever swapped, I'd have to do multiple integrals. Also, you should notice that if I use the method of disks or I use the method of washers, in each case, the representative element, the rectangle I wind up drawing, is always perpendicular to the axis, because that's the only way to get a disk or a washer. So let's go back to our region that we started this off with, where it was in the first quadrant and bounded by the curves y equals x squared and y equals 4x minus x squared. And instead of getting similar cross sections that were squares or semicircles or equilateral triangles, let's just take that region and rotate about the x-axis. This should then lead to the method of washers. So as I've done before, since I'm going about the x-axis, what I'll do is I will project the object upon the x-axis. So I'll need to know what that range of x values is. I'll pick an x value, and then I'll have a intersection between the region and a plane that corresponds to that particular x value. Now that would normally give me a line, but instead I will draw a rectangle, give it a little thickness so you can see it. And then I'll put the x on the inside to remind me that this is rectangles moving left and right. It will have an uppermost point and it has a has a lowermost point. So since this rectangle, as it goes about the x-axis, that will certainly not make a disk because there's a hole. So I'll need the outer radius and I'll need the inner radius. To do that, I'll use a little r. I'll need to know what this y value is, and I'll need to know what that y value is. Notice again on the inside is x, that what moves it, and the outside is I need the y's in this case. So the upper point here is always on the curve. Y is equal to 4x minus x squared, while the lower point, the one closer to my axis of rotation, that is always y is equal to x squared. So my small malvolume should then be equal to pi, I take the big radius squared minus the little radius squared, times d, in this case, x, because it's a thickness, there's a thickness of dx here, a small change in that x. So the outer radius is easy. It's just 4x minus x squared minus 0. That's the distance between those y values. So that's pi times, I will then have a 4x minus x squared. Oh boy, that was terrible. X squared minus the little radius, which is just x squared, and that's times dx. So the overall volume should then be just summing that up. It'd be the integration of pi times, I'd have 4x minus x squared, there you are, wrote it a little better this time, times x to the fourth, dx. I just need to know what are the bounds. What are the x values here? Clearly, they meet where x is 0. They meet where x is 0. In order to find this point, I need to know the point of intersection of the two graphs. That would mean solving 4x minus x squared is equal to x squared. And I'll leave it to you to see that the solutions are in fact 0, which we expect, and the other one where x is 2. So the integration is 0 to 2. And that's setting up that problem. Doing the actual integration is easy. You pretty much just have to distribute the products on the inside, combine terms, and then just integrate the resulting polynomial. I'll leave that to you. And that gives you a basic introduction to finding volumes with similar cross-sections, and then also the special case using the disk method or the washer method, which is just the disk method where you subtract two volumes. You should notice, though, that in order to find the volume using the method of disks or the method of washers, in each case you have an axis, and the representative element that I draw is a rectangle, and it's perpendicular to the axis. If it's touching the axis, you get disks. If it's not touching the axis, you get washers. So you might wonder then, is this what we always use to find volumes? Well, no, of course not. Mainly because we don't know what will happen when we go and set up the integral. See, we don't know what's going to happen when we take this expression and square it. You might wind up getting a definite integral whose integrand is very, very, very complicated. So, while you can write it down, you can't actually find the antiderivative to complete the problem. So, there's another way to do this entire process to find volumes of certain shapes, and that's called the method of shells, which is what I'll show you in the next video.